95 project. I did one project for both classes, and I did meta-model construction using Gaussian process regression on data I generated using this theory called Redfield theory, which basically tells you how atoms and molecules relax in the presence of a thermal bath. So this sort of stuff is relevant in questions in spectroscopy and condensed phase physics. So the first thing is I give you a brief introduction to Redfield theory. Basically, I'm just trying to tell you that you can write the time evolution of this object sigma that we're interested in as a rate equation, where this rate matrix R is a function of various microscopic parameters, and those parameters basically constitute our feature space. So the ones that we're going to look at, there are a lot, but I only focused on two that I thought were interesting, which are basically these variables D1 and D2. They're basically displacements related to the molecular structure. And each point D1, D2 constitutes a single point x sub p in the design space. So we're going to solve this rate equation for 1,600 cases corresponding to a 40 by 40 grid of the Redfield calculations in this D1, D2 space. So those were all done on MATLAB, and saved it as a mat file and ported the data over to Python. Again, all the data and all the codes used to actually do this stuff is available on GitHub. So the next thing is just a brief introduction to Gaussian process regression. It's pretty cool. It's a way to efficiently interpolate data using very little, very sparse sampling. And I give you the theoretical concept for linear extension to nonlinear models using the kernel trick. Pretty well-known stuff, and most of it is drawn from this reference 4, which is actually a pretty popular book on the subject, it seems. So I just tell you how it works a little bit. I also do this explicit parameterization of the mean, which is often called Kriging interpolation. So basically we pick a certain low-order polynomial model and use that as the basis of our GPR and go from there. So this is actually what's implemented in the code. We have flexibility to use anything up to what I call 2.5 order, which is basically including the interaction term between x1 and x2, our design variables. So the next thing is we have to pick the hyperparameters. So this kernel is a function of theta, which is the length scale over which data is correlated. So we have to pick that. The best way to pick that is by minimizing the log likelihood. So we did that using gradient descent. Worked pretty well. So I give you a few examples of how it works. We have this squiggly looking thing, sample it sparsely, and GPR actually predicts it quite well. And gives you error bars, which is important. And this is the log likelihood optimization cost that gives rise to that. You can do it for 2D, you can do it for 3D, whatever dimensions, it works well. These are just nice to look at. Next thing is the actual meta-model construction for Redfield theory. So like I said, we have these 1,600 R matrices, imported them into Python, integrated the differential equation, produces these plots. We take this plot and fit it to a exponential growth model, and we want to pull out this k-transfer, because that's basically going to be our y sub p. When you do that, for all data points, it produces this 2D contour, which in 3 dimensions looks like this, and this is essentially what we use GPR to fit. So we do this for degree 0 through 2.5. They all fit pretty well. Each one we set the hyperparameter using the log likelihood minimization, and then for all of these we also looked at cross-validation results by checking how well it predicts all of the data it wasn't trained on. So we see that the 2.5 model actually does the best. 0 actually does well too. So that's the end of the project. Here are the references. Yeah, thanks.